So now again I am putting up the RFLP. You already know it. So I'm skipping this slide because I've already covered it in the last session. So now I will talk little bit about the modeling languages. So in the modeling languages, actually, we try to understand that what kind of okay, fine, models are good, life cycle models are nice. But the ultimate question is that how are you converting these textual requirements into visual models? A systems engineer must know the conversion of these languages to the visual things. So, how can we do it? So, we usually define these into diagrams, requirement diagrams, structure diagrams, and the behavior diagrams. So, SysML is the systems modeling language. And when you define the systems modeling language, you can easily define that this particular modeling language is actually identified in almost 2001, around 25 years back. And there they talked about that how this SysML, systems modeling language, is a general purpose language for all the systems engineer, and it helps to specify, analyze, and then design all the things, and ultimately will keep on verifying and validating their systems and systems of systems also, right? So this is how this initiative has been taken by again Infosys. They are the pioneer in this model-based systems engineering. So they only initiated these kind of models. So the three categories of SysML models are requirements diagram, then the structure diagram, and then the behavior diagrams. Requirements diagram, as the name is clearly telling it, that it will be just showcasing the requirements. Textual requirements will be converted into the models, right? Or we can say the diagrams. Then the second is the structure diagrams. So structure diagrams actually helps to contribute for the P&L components. That how you will be setting up the logic and how will be coming up with the final assembly of the system. And the last one is the behavior diagrams. So this will add the behavior, or you can say the dynamism in the system, that how this will be functioning, right? So this will be adding the functionalities into the system. So the division of the SysML diagrams is in these categories. The structural diagrams are of 4 types. Dynamic diagrams are also of 4 types. Requirement diagram are just simple one. So now if you see, in these diagrams, the structural diagram, if you closely see, the block definition, internal block diagram, package diagram, and parametric diagram. Just do not think much and just think about the names. The block definition, it means it is just defining the requirements, right? Internal block, it means whatever block or whatever requirement you have defined. Within that requirement, what are the sub-requirements? So you define the one diagram, one block rather, and then you keep on defining the internal blocks within that, right? And then if you see very closely, this particular block definition diagram is basically the covers all the software, hardware, people, facilities, everything, all possible requirements. And these are the static diagrams. Static means it is just, there will be no functionality into it, but they will be used to visualize the system components and their interrelationship with other components and the other blocks. So this particular static structures helps you to understand the data objects, right, in the whole systems model. Internal block diagram is again a static structural diagram, and this particular internal block diagram actually helps to understand that what are the connectors, what are the subcomponents under this major block. After that, you see there is the term package diagram. What do we mean by package diagram? Package is basically it's a kind of classes, or you can say to define the use cases. So when you define the use case, again it is the static structural diagram only, and that helps to understand that among this particular package, what are the components and how they are interrelated. So it actually helps you to make a sense that how the architectural model will be moving on and how the logics are there. So this particular structural diagram will help you to understand the structure of the whole system, right? And to understand that how these things, whatever you have developed in the block definition diagram or in the internal block diagram, how these things are getting interrelated and how these things will be giving you the bigger picture of the system, right? So these blocks may happen in the form of packages also. Packages, that is why the name of package diagram is package. Within, how they are interacting, that complete system, complete structure will be visualized. So that is how the name is package diagram. Next is the parametric diagram. So now the question is that the way we have studied so far in all the previous modules, that how the mathematical things are involved. So again, when you are developing these things to define the logics, you need to develop some mathematical systems, right? In order to those utilizing all the mathematical rules and constraints, we utilize the parametric diagram. The name itself is defining that there is parametric, means there is the sense of some mathematical rules and constraints, right? And this basically helps to quantify the constraints. What are the total transactions? What are the number of relationships? And how these particular things are going to impact the performance of the system. So this particular parametric diagram will see that what are the inputs, what are the outputs, and how the system will function in between. So this parametric diagram is basically used to understand, to enforce all the particular mathematical constraints and the formulations and expressions. So this is how the structural things will be completed. The second category is of the dynamic diagrams. So dynamic diagrams, when you say, the name itself is defining the activity diagram, sequence diagram, state machine diagram, and use case diagrams. So these, can I say, it is coming under the dynamic behavior, right? And when you are talking about the dynamic behavior, can I say these are functioning, so showing you the functions of the systems, how the system will function. So these diagrams like activity diagrams, sequence diagrams, state machine diagram, use case diagrams. So first they will start, the basic diagram is activity diagram. Then the sequence, then the state machine, means after seeing the activity diagrams, we'll see the sequence of that, and then state machine means the transformation between the states. Now it is this state, current state. If this function will happen, the state of the system will change into the functional mode. Let us imagine that the air condition in your classroom, it is working. Now it is at 23 degree, right? Is the current state. So after some time, it needs to be moved. It may require to move to 16 degree from the working scenario. The air out. Whatever the air is coming, whatever is the cooling rate, the drop in the temperature gradient, the temperature of the outlet, everything will vary. So this current state, this right now, whatever state is having some mathematical features. And if you change this state, the particular system will transform or transition of a state to another new kind of state totally. So that things can be bring out into the models using the state machine diagrams, right? And then the last thing is use case diagrams. So if I again review it, first the activity diagram will show all the behaviors, that how it can be triggered into the systems. then it will help you to understand how this complete activity will be performed in your system. Right? So that is why it is called the dynamic diagram. Second, if you try to see the state, I've already mentioned, but again, it is just state actually is the transition between the two conditions of the system, right? So whatever states are possible, as of now, I've given you an example of the air conditioning system. 16 is one state, 17 could be in 17 degree centigrade temperature, maybe another state. Likewise, there may be several states possible. So when you are in the initial phase and you are just trying to develop all these requirements into the into the system's modeling language, how will you define all these? Now it is visible, so you can see it. But when you are in the designing and planning phase, you have to visualize all these things in advance. Then only you will be able to capture all the requirements so well, right? So that is how the state machine diagram will be used to do that.
So,
yes.
State machine diagram. So it means we have to do some sensitivity analysis. Huh?
Yes, there may be, as I told, that all the mathematical functions, all the mathematical constraints, rules, everything will be applied there. And this is how, because the moment you say change the temperature of the air conditioning system, it will be reflecting on the screen that it's 16. Is it the only change? There will be change in the whole system. The air inlet rate will be changed. The temperature of, whatever will be the enthalpy of the reactions, how this, hot air is changed into cool air, all the engineering things will be changed. All the thermodynamics and the structural temperature changes, the energy consumption, energy input, energy output, everything will be changed, right? So can I again say that whatever is happening, we are representing all these scientific things into the mathematical expressions, into the optimization rules, logic functioning, or maybe some other statistical or maybe some engineering functionalities, right? So those all things we try to mention in our model using this state machine diagrams, right? Then the last one is one is the sequence diagram also. So sequence diagram, as I already express, that it basically shows that how the occurrences of the events, or you can say the sequence of the events, how these things will happen, right? Like the moment I clicked on the remote, the first event, the second event, the visual screen will change the temperature. The third, the air inlet will immediately change its speed. Immediately the temperature will drop. The room's temperature will drop. So this is how 5 to 10 events will take place very fast. So those sequence of events is also required to be understood. And the same way you have to give the input to the whole system as well. So that can be covered in the sequence diagrams. And then the last is use case diagrams. Use case diagrams is basically we try to utilize the actors. Actors means whomsoever is the user, or utilizing this particular system, or monitoring this, or whomsoever is involved. So we try to give it as a person, as an organization, or as a facility with the software components, hardware components, everything we'll cover, and we'll try to see that how with the less technical side, how we can observe that the users are using this system, how it will, whatever systems we are preparing, how it will be visually presented or understood, that how people will interact with my system. Like switch on the AC, so the actor will also be defined when we develop the models. Though in this diagram only the systems modeling language diagrams are included, but when you develop into the software system, you will find that actors are also there, and how they are interacting with the final system, and what will be the results if the user if the user push this, how it can be. If the user you push this button, what will be the change in the system's performance? So that kind of use cases we try to develop in advance, and we try to visualize our system in that way. That if my stakeholders' requirements are this. So if again taking the same examples of flying bikes, so the stakeholder requires a bike which can fly, and from the current location to expected location, he can reach in minimum time, minimum fuel, and without any system issues, without any technical glitches, the person should reach on time. This is the requirement of the stakeholder, right? So when we are trying to develop our systems, or development while modeling all the system, we'll try to utilize those use case scenarios as well. That if the place is 500 kilometer apart, how this my system should perform, how long it will take to reach to that destination. If that location is 50 kilometer apart, what will be the speed? What will be the the
timetable?
What will be the air turbulence? How will we manage the air turbulence? What will be the temperature? What will be the other engineering aspects to what will be the other thermodynamical changes? What will be the other structural changes? So this is how we try to, and by utilizing these use case diagrams, it will actually make your system more robust, because since starting you are prepared for all the future issues. So when you are preparing your system in such a way, it will be ready to expose to any kind of situation. So it is not every time, later, nothing will be delayed here. The systems modeling, when you are modeling your system, it should be so robust, it should be so strong that you should, everything, every future possibilities can be visualized here itself. So that is how we define the systems modeling language. And the last one is the requirements diagram. Though it should be very first, requirements is the very first thing. So it should be very first, but somehow I think my slides are in that sequence, you see. Okay. R is the requirements diagram. Requirements diagram is basically, as I already told, that it is just the stakeholders' requirements, who are the key users, key actors, and users means the who are using the system. Usually people get confused that we are saying key actors, so the production people and these people are also the no, they are not the part of it. The key actors are basically the users, or you can say the stakeholder. So that by putting the stakeholder into our system positions, we'll be able to understand that how the hierarchical structure can be created, and then what should be the logical relationships, what will be the functional requirements. So this R phase, basically R phase can be fulfilled by the requirements diagram, this last one, and this requirements diagram will be helping to understand all the requirements, and this R phase only allows us to go to the F, L, and P phases. So this is a basic foundation of RFLP. So as I already described few of the things, but we can again quickly see activity diagrams, interaction among the activities of the system, state machine diagrams, which helps us to understand the possible dynamic states and the transition between states. Sequence diagrams, as I already expressed, it depicts the interactions and information exchanges. Then the use case, how the system will be interacting with the user and with the environment, right? So if I am 500 kilometer apart, what kind of difficulties I may face? Let us imagine that now I'm in a very cold temperature region, climatic region. And now I would like to travel 1000 kilometer apart, that may be a dry state, and dry in weather, right? So this is how from this point to you are now traveling to a particular altogether different environmental conditions. So how that environment may impact, which kind of changes will be required by changing in the climatic environment. That is one environment. Another environment is that let us say I'm in a similar climatic environment. Even then, from here things are different, but after some time things may be different, right? And the temperature may be suddenly increased in the same place, right? So different kind of environmental things may be feeling the effect of the whole system. So how it will be impacting the system's mission or the system's requirement, so that we can cover using the use case diagrams. And at last, again, the logic and physical architecture, again, the four blocks are there. So now after this, actually, I wanted to express few more things about this, and that is that how exactly you are going to use this particular, models. How will you develop these? So I was having just a thought here that if you are all okay, I can show you the capilla interface. So now you see here what I'm trying to explain. I am just trying to show you the interface that whatever we have studied in theory, how it can be applied, right? So the way I have explained you the four steps: the requirement phase, then the functionality, then the logical, and then the physical architecture mode. So here the same way is applied. Whatever we have, studied in theory, it is now practical. So first they have defined this phase. In this you see define stakeholder needs and environment, right? Then what will it do? Capture and consolidate operational needs from stakeholders. Then define what the users of the system have to accomplish, and then define the entities, actors, roles, and other things. In the second step, you see here it is a workflow. We are in this particular tab. Are you able to see this tab, workflow tab? We are in the workflow tab, and it is showing us the workflow, how we are going to work in this particular model. Second is system analysis. System analysis is basically about the functionality of the systems, right? Third is logical architecture, means how this particular logic will be there, interrelationships will be defined. Then the last one is the physical architecture, and then EPBS. It is little new because when you practically go and try to make all these models in this RFLP phase, what will you do at the end? You try to integrate, right? The way we have seen in the V model, RFLP was there, and then there was a lower, the last layer of that V model, and that layer was expressing that how you can integrate and implement into the system. So EPBS is basically about the phase which is integrating all the things, or in general, in layman terms, I should say, the final assembly, the final model, right? How it's going to implement. Now this is the workflow, we got it. Next is the documentation. If you want any documentation, you can do this in this particular, if you can write something, this in the class. I mean, whatever documentation you would like to mention, following things are required, right? And then you may start defining A, B, C, D. These are the required things, right? Then next phase is the operational phase. See what I'm doing, I'm just clicking on these tabs, okay? So now I'm in the operational analysis. So again, now if you see what can be done in the operational analysis, you can define the entities and capabilities. Now click on this arrow. The very important thing of these softwares are that if you forget anything, they will keep on reminding you the thing. The way we develop our logics in our mind, similar way these softwares also develop their logics in their software interface. Everything is very logically connected. So you see the very first is create a new operational entity breakdown diagram. Create a new operational capabilities diagram. Then you see the picture is shown here. Everything is 2D modeling only. Let us click on this and see what will happen. So I am now doing in the very first stage. Very first stage is operational analysis. I'm in this particular tab, operational analysis, right? And I am just going to see that how it can how I can do my systems modeling here. So I clicked on the create a new operational entity breakdown diagram. So I will just put it as like this. Okay. The short names you see OEBD. Operational, O is operational, E is entity, B is breakdown, D is diagram, right? So the full form is operational entity breakdown diagram. But you don't need to mug it up and don't need to remember, but it will automatically get into your brain. The more you practice, it will come like. So now what I'm going to do is, you see there is an option of operational entity. So I click on it and I click here. So this is the operational entity. Let us say operational entity could be. Now I would like to rename it. So I am clicking in this box. I am putting it as, let us say, engine. It is the one entity which I want in my flying bike. Now, like this, I can create as many as operational entities, right? So this is how I can, move these diagrams into the screen, and I created like this. I created many operational entities, right? Now I mentioned about the operational actor, if you remember. Operational actor means who are going to use it or who are going to interact with. So I just clicked on this and then I clicked here. So now the actor is here. So now you see the names are getting mentioned. O is operational actor, OE is operational entity. Now you see the contained in, the arrows are mentioned. In this arrows means, within this engine, these two components are coming. Within this engine, click on this contained in. Within this engine, I am saying this operational 92 is also. So now I have developed the relation. Okay. Now, if you see these constraints, if you know one very important thing I would like to mention here, if you randomly start sitting, though you may understand that how to use Capilla, that you can do. How to utilize the systems modeling language, that you can do. But if you want to develop a whole system, it means you should know the system best. If you know all the logical relationships, what are the constraints, what are the add-on things, if you know everything about the system, then only you will be the right person to do the systems modeling directly. Okay. So these are some things which I wanted to show you, because we have seen many of the things, many of the possible diagrams, right? So how it is utilized here. Now let us say I'm not interested. Okay, I'm done for this operational entities. Now I'm going again back to my class one. This part I have seen. Now I'm going to the next. Next part is operational capabilities. I'm going to develop the operational capabilities, right? So now if I say, when you click on the operational actor, it means you're going to create a new actor, right? When I click on the operational entity, it means you're going to create a new entity. But here, if you see that you already have mentioned some things. Anyway, let us create a new operational capability. Create one more, right? And for this particular thing, for this operational capability one, let us say I'm creating one actor. I'm creating this actor who will be interacting with this particular. So I'll be showing the involvement of actor with this particular operational capability, right? So I'll click on this and then I will try to connect that this particular operational capability will be taken care by this particular actor. Like this, I will create you see everything is 2D diagrams. Only ovals, rectangles, arrows, and then blocks, all these things are there, nothing else. But the way you are going ahead, you are just putting all the blocks in such a way that you are keep on defining the logic, right? Then again you go on this. And let us say I would like to define the operational activities, how these activities are in the breakdown diagram. It means one activity, within that activity, what else may happen, what else may happen, that you can do from here. You see the pictures are itself showing you root operational activity. It means what are those activities which are going to be interrelated. One, then two, I'm just putting into this. Like this, all these activities. Let us say I define the three operational activities, and I now would like to define the sequence or the hierarchical structure. If you forget it, even then you may create it. I am just putting this within this and this within this. So like this, now you see the arrows are mentioned, right? Now it is showing that what activities are within, and like that the structure can be created. Now we are going back again. So I was working on the class 1. Again I am going there. You see many other things are there. You can allocate the operators, you can define the roles, everything you can mention here, right? And then after that, when I say system analysis, in this software, the name of F, or you can say the functionality, is mentioned as system analysis. So I'm clicking on this, and you see whatever we have defined in this operational state, whatever we have defined in the timeline of V model. Remember, I shared that in the single time phase you define R, and then in the next time phase you define the F, and you do all the things which are required in the F phase. So here, whatever is required in the F phase, the moment you click, you see how the things are coming up. The synthesis is coming up like this. That what are the system functions? 3 system functions have been defined, and 3 root system functions have been defined. 2 operational activities are there. So now I am going to define that how it cannot. So you can do this. The moment I clicked on it, it is connected with the class 1, right? So now the connections, the logics, all things are started appearing. You may define more, actors, missions, capabilities. So like this, if you keep going on, some projects are already have been done. One inbuilt model is there in flight entertainment system. So in one of my, during my research work, I have developed one, this thing, uh, one in-flight air conditioning system. It was during the COVID time. Actually, during the COVID time, there was a problem that, even if the virus will get into the air within the air flight, and then all the passengers will get infected by the COVID. So just to consider that how the filters are working in the air conditioning system, and how we can, without even touching, without having, it was assumption that everyone is wearing the mask and no air is mixing directly into the air which is flowing inside the cabin or inside the fuselage of the aircraft. So after taking some other assumptions, we developed one particular, systems, that how this life cycle model will be working, and how these models, so SysML models were used for that particular thing. So here, if you see this particular, model where which is inbuilt here, that how it is working. So you see the operation analysis part here. You see how things have been defined. Okay, it is not here. I think AIRD will work. No. But this is greater than yes. Yeah, exactly. So right beside home state or operational activity, right beside operational activity, there is little greater than that. Okay. No, I think this. But if you have, yes. Yeah, I think it should go. Yeah. So now you see that this is a small, example that how things are working. Now, if you see closely, you may seem that it is just oval blocks and arrows. That's all. But when you go into the closer thing, you will realize that this is not that's all. You see how their interaction between entities it is because in flight, so how the audio announcements are interconnected with the landing timelines, right? How the movies and the safety instructions and the ambience music, how the things will be happening when you are talking about the in-flight entertainment system. So several announcements to be made during the time you may be hearing some music or maybe watching some movie or entertaining with other things. So visual and or I mean audio and video both things will be coming on. So what are the actions you will take? Movie selection, music selection, then whatever movie you selected will start playing. Whatever music you have selected, it will start. Then the moving map, how you are, moving also, you will be just having some map also that where is your location. So multiple things, and in between some, flight announcements will also be coming up. So this is how many things are happening, and everything is considered here right away. And here, if you see actors, there are the actors. You see the passenger, aircraft, and cabin crew. So they divided the three sub, you can say the three packages, right? And this is how the sequence of whole work will be mentioned here. So this is just one example, but I would like to give you a home assignment. One is thing you can, though I am showing you the Capella, and there's a freeware also. You can download it in your systems. It is just I think just 5 minutes work. Not it will not be taking much space as well. So my thing is that most of you are mechanical engineers. So just take a small mechanical system. That can be just kind of you can say a moving chair. Small example of moving chair. Define five things and try to come up with just a small things. I know you will not be very robust on mathematical constraint, defining mathematical constraints and elements. But even then, you can just try to define the actors, the user of the chair, one actor, maybe you can say about a wheelchair, and then you may say that what are the possible things, what are the if I say a person is handicapped and that fellow wants to move on the chair, wants to you to develop a chair for me, and now let us say it's a new kind of chair, right? So when it is a new kind of chair, how will you start as systems engineer? It is not there. You may have some information in advance, but how will you plan? How will you manage this engineering system planning? That is the role of systems engineer, right? So in order to do that, you have to develop all these diagrams. Just two to three diagrams you try to do on your own. Then you will get an insight that how these softwares can be utilized. And at the end, you will be coming up, I think, with you will be coming up with the physical architecture. Let us quickly go to this and then just try to see that how you see the unit network adapter, though they have defined a lot of things because they know their system best, so they could able to define all these things, network transport, network setup, configuration, test, instantiations, then implementation and behavior components, remote diagnostic equipment. So let us quickly see once that how they have created. Now you see this particular model, right? Why I'm showing this? That will be because in the next module is based on this only. So here you see that how many models are, how many diagrams are there, and how the logical relationships are defined using these arrows. If you try to just, I have just zoom in and zoom out, right? So I'm just zooming in, and you see this blue arrows, they are actually logically connected, that what will be done first, what will be done the next action, what will be the next event, like this, all these activities are related. So these kind of systems model actually help us to understand, basically do the verification and validation. Whatever you are doing here, is it functioning there or not? If this particular thing is not functioning, what else will impact in the whole system? If this is happening, this event is occurring, what are the other events will take place simultaneously? So all these kind of verification, or what will not be working. So everything we'll test, validate and verify in this particular phase only. But you see, everything is in the model format only. Nothing is in physical mode. We are just struggling to verify and validate all these things. Usually when we use this kind of softwares for the systems modeling in our um, you know in industries, it is not the standalone software. There will be multiple other softwares. You will be this particular one systems modeling, the programming tool will be integrated with the CAD models, integrated with the all components CAD models, all the electrical components softwares, all the electronic softwares, everything will be, in fact, it will be connected with the bill of material also, right? So you can say, if I talk about industry language, I'll say it will be connected with ERP, it will be connected with PLM software, it will be connected with 3D modeling, the mechanical design softwares, it will be connected with the electrical design softwares, it will be connected with the software design softwares. So all the digital softwares will be interconnected at one forum. Can I call it that this is a collaborative engineering approach? So this is how, when we do these things in industry, when you are really going to develop a particular product or a particular system bringing to the market. So now you see the what is happening backstage. So all the engineers, all the designers are there integrated at one single digital platform. And whatever change you will create in one particular point, it will be creating an alert to all the stakeholders. Now again, I'm using the stakeholders. So these stakeholder term is to address all the people who are working on this system, right? So everyone is now working together on the similar, with the similar information, or you can say the real time information. I, let us say, change one raw material in my one of the product component design. So now changing that raw material means that raw material properties are different. In what sense? Maybe it's the temperature, capacity, the brittleness, and then maybe the flexibility, then the many other features may be there which may change, right? The temperature, the particular raw material may be conductive. Now it may be non-conductive. So if it is non-conductive, what could be the impact to my remaining components of my engine, or in the in the other pipes? So everything will be investigated here itself. Now there must be a question that whatever these physical models are, whatever models you are able to see, these interconnections are shown, how they are functioning. The moment it will function, everything will be showing in different color maybe, and then it will be showing you the roots, the issues will be highlighted. One very important thing to mention here is that the moment I will see a change, it will become a question mark. Okay, fine, this is a change and this is how my other system or subsystem components are going to be impacted. This is that is the reason why we work in the integrated format so that with time from one place to another place, the information flow will be immediate. And that information flow help us to come up with the robust system and with the minimum time and with the minimum efforts. Now you may have a doubt in your mind that who will do all this? Can only one person will do all this? Actually, that is the reason. I mean, when you define, because I am a systems engineer, means I know the system. But if you ask me to, create a 3D electrical looms design the electrical looms in a software, I may not be able to do that. I may not be capable to do that properly. But I know how to manage these engineering work. So, as a systems engineer, the role of a systems engineer or the systems engineering model role is how to manage all these humongous engineering tasks. So, you see, all the engineering is there on this particular screen, and behind all these blocks, there is the mathematical constraints, various mathematical models, constraints, the behaviors, the logics, the functionalities, everything is involved behind it. Okay. So now one I'm going to the to one more detail about it, that we talked about models, we talked about systems engineering, we talked about the life cycle models. What is the role of systems life cycle model with the product life cycle model? Any thoughts? Many industries we connect. This is just one part. This systems modeling or systems diagrams are just one component of the whole system, right? We have just modeled, we have created the logical things, functionality, we have checked, we have developed all these things on paper or on the digital models, all fine. But there is a other workforce as well, other engineers also, mechanical engineers, electrical engineers, electronics engineers. Then you will maybe having some software engineers, then the structural, many other things may be involved, right? So now my question is that every person is involved to support the modeling of this systemal model. It is not the role of just one person. It is the whole team who contributes to these digital diagrams, right? It is not the capability of just one person. It is multiple people are involved to come up with these models, right? I'm just showcasing that how things happen in this systems modeling languages. So these systems modeling languages, again, I will say, this is not just a 4 line block. It itself is having a coding behind it. That how whenever you call this rectangle, how this, let us say, you are calling a particular model, like let us say to define the operational activity, right? Let us say in particular place, I'm going back again. Let us say I'm going to operation assist and I am creating, uh, let us say it is like this. Okay. So now I created this. So can you say it is just 4 line block? No. There is a very detailed software coding part behind it, where everything related to this particular operational activity can. What I did, I just double click on it, and the moment you double click on it, you will get all the things, what mode it is. Then you may define many more things inside it. You may define, here it is nothing I have mentioned, so it is blank, but you may have in real time cases, you may have many more things listed here, and what to connect, how to connect, everything is planned, everything is coded in such a way that this particular functionality will be open up wherever you click on this particular whether it's an oval or it's an arrow. So there is a programming behind each particular diagram. And this is how we are going to logically connect it and show, able to show the functionality of these systems, right? So I hope that by seeing these diagrams, you'll get a real feel that how things actually happen